My name is Zuhaib. I'm from Ghent University, partly related with Imec R&D group. Today I'm going to talk about the fusion between multispectral or multimodal images, uh, more specifically with the color and thermal images for pedestrian detection. So this is the layout of my presentation. In which we will first discuss or see that why pedestrian detection is important and why fusing is important in this scenario. Um, then we will see that what are the possible ways to do the fusion and the methodology that we choose to do this fusion by exploiting an existing method, which is joint probabilistic data association. Then how did we exploit this method? Some experiment setup, result, and the conclusion. So we all know that pedestrian detection is really important in several applications. Just to name a few, like autonomous vehicles, advanced driving systems, and so on. In such systems, there are multiple sensors used, like RGB camera or color camera with other sensors. In most of these cases, the main decision in such systems comes from the color camera. With this said, I'm here referring unfortunate incident which happened in America. So this scene is actually from autonomous vehicle just before the accident, and probably none of us can see something in the scene, but actually there is a pedestrian, and well, not on this slide, but if you see the images, there are some feet visible of the pedestrian, and after some time there was the accident. After this investigation, the reason was the system was unable to detect that there was a pedestrian properly. So in the following year, AAA, which is American Automotive Association, they performed several tests on several products of autonomous vehicles, and they concluded that none of the existing methods was able to work properly for pedestrian detection, especially in the night. And the reason was that because the main decision comes from color images, and if color image cannot see anything, that means the system cannot see anything either. So what could be the solution? Solution would be to use another sensor, like a thermal visual sensor, because visual sensor provides much more information, but thermal camera itself has some limitations, such as it does not provide you color information or texture information. So we cannot use only thermal camera, but it's better to use both sensors at the same time and fuse them. Now, whenever we talk about fusion, especially for heterogeneous visual sensors, they are classified in three ways. One is early level or called pixel level, where each pixel of both sensors are aligned together, but it has a problem. Problem is that this creates another requirement for well-aligned sensors calibration, and which is another problem. Then picture level, in this case, it's one of the most popular methods, because nowadays normally all the two-stream neural networks fall in this category, where we can fuse the features at early level, intermediate level, or at late level. But this also requires some sort of calibration or alignment between the units. Then the third is decision level. In this case, the processing is applied separately on both images, and then the decision is fused together. With this method, there are some advantages, which is it does not require fine registration, because if there is some error in the calibration, it can be adjusted in the model separately. Why is it is more important? This is because there are many differences in the both sensors, like in terms of field of view, in terms of image size, in terms of frame rate. So it's really hard to calibrate both sensor data perfectly. Second advantage is it does not require retrain, so we can use off-the-shelf detectors to do detection. And then another advantage is that it is all possible to model this decision level fusion methods, so that if one of the sensors is unavailable because of any reason, then it can able to handle it. So by saying this, we propose this kind of method. So we use IR images or thermal images, RGB images, off-the-shelf detectors, so does not require any retraining, and we will fuse them in a modified method in such a way that those detections are taken into account, including the sensing conditions. Why? We will see. And in the end, after this fusion, because we take all the detections, regardless of detection score, it's quite possible that there will be multiple detections that overlap each other. So it's better to use non-maximum separation to solve this problem. So why it's important to consider the current sensing conditions? Because it affects both color images and thermal images as well. We are familiar with thermal color images because unavailability of the light, but it also affects thermal images as well. Why? Because of the unavailability or availability of ultraviolet light. Like you can see, there is a pedestrian here, and all of the pixels inside that object or pedestrian are darker. While on the same day in the evening, because there is no ultraviolet light, you can see that all the pixels inside the pedestrian is lighter or light pixels. So it's better to use this sensing condition into account for better results. So how do we do that? By exploiting an existing system. So an existing system, which is a JPDA, actually a tracker, that performs the association between the objects in measurements, and we can exploit this part of the tracker to perform fusion as well. Why it's better? Because it considers several things, including detection probability, false detection density, and for tracking it uses Kalman filter and measure a distance using a normal distribution by a covariance filter. So if we see these objects in the measurements in the image plane, seems that this measurement is quite close to this object. So this should be associated with this one, but this is not the real case because it depends upon this tracking as well. So in this try example, the normal distribution is created by somewhere here. So that is using the innovation Kalman matrix, and then the association is done accordingly. So how this is able to deal with a misdetection? By using an image neuronal detection and considering the false detection probability. So we can exploit this part of this method to work as for the fusion. So what we do is here, we use the same method just by replacing the association part with the help of a multivariate distribution. So one distribution comes from thermal image detections and another comes from color image detections. We also consider the same thing like detection probability, false detection density, but the distance is computed using a multivariate Gaussian distribution and their covariances in the distance. So in the same way, we also use the null measurements to compensate for the null detection. So in this example, we can see that these blue are the detections from or measurements from color images, and red are from the thermal images. So again, if we see in the image plane, and if the images are really aligned, so we can see that this measurement should be associated with this measurement, but this is not the case. Because if we consider this distribution, then these two will be somewhere here, and these two will be somewhere here. With this consideration, the assignment of these or association of these measurements will be something like this. So after all this said, how can we measure the performance of our system? So normally we use some performance metrics. In there, we use precision and recall, which defines the total number of detections and misdetections, and then mean average precision, which is the graph between the recall and precision by changing the threshold. So we get something like this kind of a curve, and the area under this curve is called average precision or mean average. For dataset, we used a FLIR dataset that's from FLIR company, but it was not aligned. So in this publication, the author aligned it manually, which is not still like perfect alignment, but still some alignment. So with the comparison, with the dataset, if we use both RGB and color images, these are the results of our proposed fusion. This is a well-known state-of-the-art method, MBNet and MLPDNet, which performs quite well, but still our method surpass this in both precision and recall and mean average precision. Now, when there is only thermal image and the color image is missing, so MBNet normally, which is a deep neural network, it was not trained to handle these kind of situations, so you can see the performance decreases quite rapidly. While MLPD, which is especially designed to handle these kind of situations, and it was trained enormously for these situations, so still it can work a little better than the proposed method. Again, the same, if the RGB is available and thermal images are not available, then you can still see this method performance is really degrades, while this method is still able to handle at some level. But overall, the performance of our proposed method is much better. So by considering all these results and methods, it seems that our method performs better than existing methods. It has the ability to deal with the situation when one of the sensor data is unavailable, and more important, that does not require retraining, because we know that normally deep neural networks or CNNs require a huge amount of training, which requires huge annotated dataset, which is a separate problem. And this can be really implemented easily by changing few parameters from a very small annotated dataset. So I conclude my presentation with this. Thank you for your patience.